Thank you very much, and thank you very much for the invitation to be here. It's been a really interesting symposia so far. It was great to meet so many of you. Okay, so I'm going to talk today about some of the methods we've been developing for automating calculations on a very wide scale. And so just to give you a bit of context about why we're interested in doing this. So I'm very interested in my group in materials discovery, and this is our kind of typical approach that we think about, which will be familiar to many of you, when we kind of trying to analyze a new material. So we might take a crystal structure, we do a DFT calculation on it, we get some DFT outputs, in this case a band structure, and then maybe we do some kind of post-processing. In this case, we are calculating the absorption, and we're comparing it to the AM 1.5 solar spectrum. And this might be something you would want to do if you're, for example, trying to find a new solar absorber. So this is very nice on one material, but over the last decade, high throughput calculations have emerged as a very powerful tool for kind of doing this on a wide scale. So here's just some examples of high throughput studies. We've had kind of people doing 1,000 phonons. That was back in 2018. People have been looking at Raman spectra, band gaps, elastic tensors. And many of these properties have kind of made their way into these large data sets, which are now kind of 7 or 8 years later actually proving incredibly useful for machine learning. So I think there's a very important use here for some of these high throughput studies. Now, the issue as we see it is that these sorts of high throughput approaches are almost entirely dominated by these very big materials databases and consortia. So things like the Materials Project, AFlow, Nomad, and Alexandria. So I'm from the Materials Project, so I'll just maybe introduce that a little bit. Can I ask, has anyone not heard of the Materials Project before? Could you put your hand up? Okay, so there's a decent amount of people. So the Materials Project started back in the early 2010s, and the goal is really to compute the properties of every known material. And so it was started out of Berkeley, and this is the current website. So we currently have about 250 registered users. We have about 250,000 registered users, about 150,000 inorganic compounds on there. For these, we've got many different properties, things like band gaps, band structures, dielectric constants, elastic constants. And it's growing all the time as new materials get added. So it's very nice. You can kind of put in a composition and search for materials that might match that composition or that sort of property. I think the other very nice thing about the Materials Project, and I think the reason why it's gotten so much use, is that we have a load of different applications on there which can help you kind of discover and identify materials. So tools for plotting phase diagrams, tools for looking at interfacial reactions between two materials and whether any secondary phases would emerge, and kind of many, many other more utilities on that website. So if you've never come across it before, I'd really encourage you to check it out. I think if you're a material scientist, it can be very useful. Okay, so that was a very whistle-stop tour introduction to the Materials Project. In fact, the Materials Project website, what you see when you go on there, that's really just the tip of the iceberg in terms of what we've had to develop in order to deliver that to you. So underneath the hood, there's a whole range of software packages, what we call the Materials Project software stack, which allow us to kind of do this sort of high throughput calculations and present it to you at scale. And so I'm going to talk a little bit about one of the tools that we've been developing called Atomate 2. So our goal with Atomate 2 is to try and make high throughput calculations, and by that I mean the ability to run many systems, tens, hundreds of thousands of systems at once, accessible to everyone, not just these big high throughput platforms. So I guess one of the goals that we would like to be able to do, our ideal system, is say, what's the elastic tensor of gallium arsenide? We ask this question, we do something, and then it gets sent off and we get the results back in our database for us. And if we have something that looks like this, then what we can start doing is we can start just picking as many materials as we want. We might say take all binary oxides, replace oxygen with sulfur, calculate all of these different sets of properties, and it really shouldn't be any more difficult to do that if we have a good workflow system in place. And so that's exactly what we've kind of done with Atomate 2. It allows us to calculate the properties of many materials, put them into a database, and then you can kind of analyze your results. And so Atomate 2 essentially is a library of computational workflows. And so we have many different calculation types, from just simple things like geometry optimizations and band structures, got a whole range of different functionals. It's very, very easy to customize all of the settings, all the way up to kind of more complicated properties, things like looking at electron phonon coupling, looking at finite temperature phonons, looking at lattice thermal conductivity, and I'll talk about some of these in a little bit more detail in a second. So we have over 100 workflows. Each one of these is essentially a mapping from a very high-level description to a series of low-level tasks. And so this is an example of the harmonic phonon workflow. Many of you will have done this by hand. And so essentially we take a structure, we relax it, we create a supercell, and in fact, technically we do increase supercell size to kind of check for convergence. We calculate the dielectric constant so we can get the LOTO splitting, and we run a series of displacements. And you can see all the user has to do is submit a structure and say, run this one workflow, and under the hood, all of these different steps will be done, and then we can pull out the heat capacity and phonon band structure and things like that at the end. So when we started doing this, this Atomate 1, let's say, was really focused on the VASP software. And if I'm allowed to say this in this room, we have now extended this to other DFT packages as well. So we have support for a wide range of DFT packages: CP2K, FHI AIMS, Abinit, QChem. We're currently adding Quantum Espresso, and we're thinking about other ones as well. So if you're interested and you want to help develop a DFT code and you think it could belong in Atomate 2, let us know. What's nice is that many of the workflows are actually code agnostic, so it doesn't matter which DFT calculator you use. So for example, the phonon workflow, doing a relaxation or getting a static energy, that's independent of what DFT package you might want to use. So the workflows are written in a code agnostic way. When you run them, you can just decide which DFT calculator you want to use later on. And this also extends to machine learned force fields as well. So actually we have support for many of the emerging machine learned force fields. This is kind of getting a bit tedious now to stay on top of which force fields we keep at Atomate 2, just because there's another one every week or so. But we have all the popular ones: MACE, ORB, Equiformer, UMA, things like that. We also have support for the VASP on-the-fly machine learned force fields, and if you want to have a kind of bespoke Gaussian approximation potential or a NEP model, we also support that as well. And this is just to kind of go to the point that many of these workflows support multiple DFT packages. So basically, VASP is supported by almost all of the workflows. But if you look at, for example, FHI AIMS, that also supports a huge range of the workflows that we have in there as well. And this is really important to us because it means that we can also benchmark different codes against each other to make sure that we've got the same settings and that our results are comparable. Okay. The other thing which I think having these interoperable workflows enables is specifically when some DFT packages, for example, might do better in some cases than others. So the example that I want to give is in defect workflows. So the typical thing we would do in a defect workflow is we would take a crystal structure, we would introduce a defect, we would do a relaxation, and then calculate the defect formation energy. And typically we're using hybrid density functional theory for defects in order to get the correct localization of the wave functions. And this is very expensive in DFT. We're doing large supercells at hybrid level of theory. What we do in this case is our defect workflow by default includes a CP2K gamma point relaxation, which is very fast, followed by a VASP 222 gamma point relaxation. And actually you don't really have to do anything. The workflow as a whole looks the same. All that changes is this one calculator which calculates the defect formation energy. So it allows us to kind of mix and match DFT packages in order to get the best of what we're interested in. So this is, it's a bit hard to see, but this is just an example of the code that you would need to run in order to relax a crystal structure and calculate the band structure. So this will do a whole series of calculations. Most of this code is just importing a structure from a file, and then we just have one line which essentially creates the workflow itself. So it's Python based and it's very quick and easy to run. That was kind of creating the workflow object. When we want to actually run it, we can either run it locally on our kind of local machine or on just a single compute node, or if we want to manage these calculations at scale, we've developed a package called JobFlow Remote, which allows us to automatically orchestrate all of the calculations on supercomputers. And essentially the code for running with JobFlow Remote, you would just run this one code from your local computer. It just says submit workflow. It gives the workflow object and then what cluster you want to submit it to. And this automatically handles SSHing into the cluster, submitting the job, writing the input files, once the calculations run, downloading everything and putting it into the database. And so you can run this command 1,000 times with 1,000 different structures, and it will also do smart things like job packing and trying to do as many jobs in a single compute instance. So it makes everything much easier than doing it by hand. The very nice thing, I think, is that, and I stole this slide from my old boss, Anubhav Jain, but by using Atomate 2, you really benefit from the expertise of, I would say, probably about 50 research groups and generations of PhD students. Many people have worked out the best way to calculate a particular property, for example, the default settings for phonons and things like that. You can benefit from all of their experience without having to implement it all yourself and kind of learn from the mistakes from others. And as more codes get added, you can benefit from those as well without, I don't know, it really reduces the barrier to entry for a lot of these problems. Okay, so Atomate 2 now powers the materials project database. So there's constantly new calculations being added. Currently, they're trying to recalculate all of the energetics and band structures with R2scan, and that's all been done with Atomate 2. So it's been tested on a wide scale. So if you want to use it, you can also have some kind of confidence that it is a robust package. So if you're interested, you can try Atomate 2 today. It's just a Python package. We have a very detailed documentation, but we also have a help forum as well. And if you get stuck at all, feel free to email me, and I'm very happy to help diagnose any questions. Okay, so I now want to talk about two areas which we've been automating calculations, which I think are very useful for kind of materials discovery and related to the things that we've been hearing about this week. The first is about understanding thermal transport, and the second is about calculating electronic transport. And really our motivation for doing this is that these properties are very intensive to obtain, so we want to do it in a way which is amenable to this sort of high throughput approach. So I'm going to start talking about thermal transport. And as this kind of graphic shows, here what we're doing is we have not developed this code ourselves. We're using a package called High-5 to do a lot of the work. So some of you may have heard of that before, but I'll explain a little bit about what High-5 does. So the typical approach to obtaining force constants in materials, we take a cell, we then have to displace some atoms away from their ideal sites, and we calculate the forces on all of the atoms. This allows us, we repeat this for every atom in the cell in all the directions. Obviously, you can reduce this by symmetry, but this allows us to obtain, the second order force constants for a material. Now, if we want to go on to third order force constants, and we heard a really good explanation of why we would want to do that yesterday, when we're interested in anharmonicity, so things like if we need to know the phonon lifetime, then the kind of naive approach to doing this is you replace two sites. Now, unfortunately, as soon as you've replaced more than one site, you've broken the symmetry in the structure, so all of the other sites become inequivalent, more or less, and suddenly the number of deformations that you have to calculate grows exponentially. So even for kind of relatively simple materials, this can quickly become thousands or hundreds of thousands of deformation potentials depending on of deformation calculations depending on the supercell size. So what this package High-5 does is an approach where you can use statistical learning to displace all of the sites in a structure all at once and use an algorithm such as compressed sensing to fit all of the force constants simultaneously. So it means that rather than having thousands or tens of thousands, you can now just get away with 5 to 10 structures and still obtain pretty reasonable force constants. So it's a very powerful method. What we wanted to do was kind of automate this and make it accessible because there are a lot of different settings, cutoffs, convergence parameters that you have to test, and it can be a bit tedious. So this is that Atomate 2 High-5 workflow. It's relatively complicated. It includes a whole range of convergence checking and obtaining kind of downstream properties as well. So we don't just do high five, but then we also go on and calculate things like thermal conductivity afterwards. So the properties that we can get from this are things like the free energy, entropy, heat capacity, thermal expansion, and lattice thermal conductivity. We also are able to do this, we are able to get temperature-dependent phonons. So it's not exactly the self-consistent phonon approximation that we heard yesterday, but it's something related to that. And so here's just an example of some benchmark properties. This is looking at the thermal expansion for a bunch of binary systems, and this is looking at the lattice thermal conductivity. And again, you can see that this is against experiment, and we see pretty reasonable agreement compared to experiment. I mean, there's all the usual caveats here. This was all done using PBE, exchange correlation functional. So there's a recent paper showing that you can get 10 to 20% difference in your thermal conductivity depending on your exchange correlation functional. But I think it's quite nice, and it's fully automated, and all of this was really done extremely quickly. The other nice thing that we can get, because we're getting temperature-dependent phonons, is we can have a look at phase transitions. And so here we're looking at zirconium in this BCC structure, and you can see that as you increase the temperature, your soft mode renormalizes, and at some point it becomes real rather than imaginary. And if we compare that point compared to the experimental transition temperature, you can see that we're within 200 Kelvin, which is actually not super bad for this material, especially, again, considering all the functional choice and things like that. So yeah, so this is kind of one thing we want to move now with this sort of approach, is to being able to calculate temperature-dependent phase diagrams. And so there's a lot of, I think, scope for us to do that based on the speed of these calculations. And just to highlight the speed, this is looking at the speed up that we would gain compared to the phono 3pi, or compared to the naive approach of calculating all of the force constants simultaneously. And for most materials, it's at least 100 times speed up, and for some materials, it's close to 1,000 times speed up compared to the naive approach. So we really do save a lot on computational efficiency. I guess at this point, it would be remiss to say that there's an even easier way to get computational speed up for these materials, and that's towards using machine-learned force fields. And I'm not going to talk too much about this, but one thing we've been looking at is these universal force fields. The issue is that when you use a universal force field, you get this kind of considerable systematic underestimation of the phonon frequencies. And people are trying to account for this, but in most cases, it's still there. So this is looking at MACE MP0. This is just for indium arsenide and boron nitride. You can see compared to the dashed grey line, the DFT, MACE is considerably lower. And when you go on and calculate the lattice thermal conductivity for these systems, you see quite a considerable spread in the lattice thermal conductivity. What we've recently shown is that just by taking one structure calculated with DFT with just some random displacements, you can use one of your high-five structures, for example. Fine-tuning on a single structure, you can get rid of all of those discrepancies, get very nice agreement to DFT, and also we can, if we do this for a bunch of materials, we can get very nice agreement on the lattice thermal conductivity as well. So I think by combining these machine-learned force fields and the high-five approach, it could be a very quick way to get lattice thermal conductivity. Okay, so that was a quick foray into our work on lattice dynamics. I now want to talk about our approach we've been developing for electronic transport. So the transport of electrons, and here we're thinking about band-type transport, is governed by the Boltzmann transport equation. And so in this equation, we have three terms which are important. We've got the energy, which is very easy to obtain from a DFT calculation. We have the group velocity, which is again very easy to obtain from a DFT calculation. But we also have the lifetime, and this is very hard to obtain. And so there's been a whole range of methods proposed for calculating the lifetime of electrons in solids, going from just using a constant lifetime and hoping that this gives you some sort of reasonable results. But obviously when you do that, the results that you get can be scaled arbitrarily according to what lifetime you pick. There's techniques such as the inverse density of states approximation, where you say the lifetime is scaled versus the inverse density of states, which makes sense physically. If you have a larger density of states, you've got more states available to scatter into, so maybe your lifetime will be lower. But again, you still have to pick a reference lifetime, and so your results can be arbitrarily scaled again. On the other side of the spectrum, you have methods based on density functional perturbation theory, often combined with Wannier interpolation. And these are very accurate methods for obtaining electronic transport. The issue is that they're extremely expensive. And so what we wanted to do was kind of bridge this gap and develop a method which was close to the accuracy of density functional perturbation theory, but at a computational cost much closer to these inverse, to these constant lifetime and cheaper approaches. And so happy to say that we did that. So our method AMSET essentially allows us to explicitly obtain the scattering rates whilst remaining computationally efficient. And then when we do that is that we use scattering matrix elements which are based on easy to obtain materials parameters. So things like, so in AMSET we have support for at least three different types of scattering mechanisms: acoustic deformation potential, scattering from ionized impurities, and scattering from polar optical phonons. We also have piezoelectric and some others as well. But to calculate each of these scattering rates, all you need is the deformation potential, which is relatively straightforward to obtain from a series of strained calculations, the elastic constant, which is again easy to obtain. And in fact, I showed before that we have calculated thousands of them for the materials project. The dielectric constant, which is very quick, and also the polar phonon frequency, which again we can get from a dielectric constant calculation essentially. And so we've created a workflow for this code in Atomate 2. We have to obtain all of these different materials parameters, and so the workflow is itself quite complicated. And you can see this is just a schematic of it here. This is going through the different stages of obtaining all the different components. Once we've done this, we can go on and calculate electronic transport in materials. So this is just some results for gallium nitride. The black lines, so the black triangles, those are the experimental results. The black line is the total result from AMSET. And I should say that this was obtained once we have all the materials properties calculated from DFT. This took about 10 minutes to run on my laptop, so it's very, very quick. What's nice is that you can, and again, I should say this is fully first principles inputs. There's no fitting or tuning parameters here at all. And what's nice is that you do actually get kind of insight into the scattering physics of the material. So you can see that there's a crossover between ionized impurity scattering at low temperatures and polar optical phonon scattering at high temperatures. And when we can compare this to the kind of result predicted from these constant relaxation time methods, which are also quite popular, you can see that that doesn't get the temperature dependence or the magnitude of the mobility right at all. So we're doing much, much better. And this wasn't just one material. We tested on a wide range of compounds like gallium arsenide. We've got silicon here. This material is tin selenide. This is an anisotropic material. And what we show here is that we're actually able to reduce the correct anisotropy of the mobility. So the mobility varies significantly between the B and C directions, for example. The red lines are results from density functional perturbation theory combined with Wannier. So this was compared to EPW calculations. And we get pretty decent results compared to EPW, especially given how cheap and how many approximations there are in our methods. So we're definitely not trying to claim that it's as good as those methods, but it's just one quick screening approach that gets you close to them. Okay. And again, this is just some results that we did across a wide range of materials, showing that we can basically reproduce the experimental mobility for single crystals across a wide range of compounds, even for some very low mobilities like copper aluminium oxide, where you're right on the border of carrier hopping versus band-like transport. It seems to do reasonably well. And just in terms of the timings, so here we've got the time taken to do different parts of the calculation. So the solid bars, those are the inputs, the DFT calculations, and the kind of hatched bars, that's the actual transport calculation. And you can see that this is a log scale as well. So constant relaxation time is very cheap for both parts. Our work, the most of the computational expense is calculating the first principles inputs. Actually obtaining the transport properties is very, very quick. And this is kind of some sort of Pareto front here where we show that density functional perturbation theory plus Vanier is very accurate. I mean, that's our reference there, and our work is within about 10% of density functional perturbation theory plus Vanier, but about 500 times computationally cheaper. So if you're interested, again, AMSET is available open source. It's also a Python package, although some of it's been written in Number to make it a bit faster. And we have a help forum if you're interested in trying it out. There's some good tutorials there already. Okay. So I just want to give you one quick example of how we've been using AMSET to understand the behavior of transporting materials. So I've mentioned the mobility. It's a kind of key materials parameter which has been often used to understand materials. It's relatively independent of carrier concentration, and it's got this relationship to the conductivity here. So the temperature dependence of mobility is something that I want to talk about. And this has been used since about the 1930s to understand the quantum behavior of materials. So going back to this seminal work by A.H. Wilson in 1931, where he derived an expression for carrier mobility given the assumption that electrons are scattered by lattice vibrations. And what he found was that under this assumption, you would expect your mobility to have this T to the minus 3/2 temperature dependence. So it decays with this kind of power factor. And what was very nice about 25 years later, when we finally were able to grow high quality single crystals of germanium, some of the crystals showed very nice agreement to the mobility trend that he predicted. And so I think this is very nice. This was actually, Wilson's work was the first time that valence and conduction bands had been modeled as separated by a gap. He was the first work to think about impurities as the source of free carriers and as lattice vibrations as the source of scattering in these semiconducting materials. And the results did very nice and predicted some experimental trends. Today, people are still thinking about this temperature dependence of mobility as a mechanism to give you insight into the scattering physics. So for example, there's been a whole range of different temperature exponents proposed, which are associated with different scattering mechanisms. So for example, I mentioned acoustic or optical deformation potential, which has this minus 3/2 temperature dependence. We have polar optical phonon scattering, which was proposed to have a minus 0.75 temperature dependence. And if you see a 3/2 temperature dependence, that's meant to be a sign of alloy scattering. Now, the issue is that all of these approximations were derived from simple models where you have a single isotropic and parabolic band structure. And yet in some communities, especially the thermoelectrics community, I think, these are still applied as a kind of rule to determine what type of scattering is dominating or limiting your mobility. So we wanted to kind of understand whether this was a valid thing to do. And as these theoretical tools like density functional perturbation theory plus Vanier, as these have become developed, we've now been able to get results in very nice agreement with experiments. And so we wanted to use these as a kind of fundamental insight into this behavior. So this is just to show that density functional perturbation theory plus Vanier agrees very nicely with lots of different materials across scattering types, across different band structures, and across different temperatures. The issue is that when we were looking at what kind of started this whole thing is when we looked at one example material, tin selenide. This is a kind of prototypical thermoelectric material, and its mobility has this T to the minus 3/2 temperature dependence, and this is reproduced very, very nicely with the computational methods. So for a long time, everyone had assumed that this was limited by deformation potential scattering. But when you actually look into the calculations, it turns out that polar optical phonons are what are dominating, not deformation potential scattering. So this is one of the most well-studied materials. We thought, what's going on? Could there be more out there? And so we wanted to answer this question, does the temperature dependence of mobility actually tell us anything about the dominant scattering mechanism? And so the first thing we did is just did a review of all of these high-quality calculations that have been performed to date. And this is what we're showing here. On the x-axis, we've just got the temperature dependence. And on the y-axis, we've just plotted them based on effective mass. This is just to kind of show out the points. And the different colours of the point show what mechanism is dominating. So for example, the pink is the deformation potential, and the teal is polar optical phonon scattering. And what you can see that for a single scattering mechanism, let's say pink, you can basically span the entire range of temperature dependences from minus 0.5 all the way to minus 3. So from this very quick assessment, we thought, it's really not safe to assume a particular scattering type based on the temperature dependence of mobility. But we wanted to understand exactly what was going on. So then we turned to our AMSET method. And the first thing we did is just take a very simple model, a single parabolic band, and took one of these simplified scattering mechanisms, the polar optical phonon scattering, and we just adjusted one single parameter, which is the polar optical phonon frequency. And we found that just by varying that one parameter, you can essentially get the temperature dependence to vary across this -1 to -3 range. And if you do this at higher temperatures, you see the same effect. It's just kind of less pronounced. And so, we really think, and it's very obvious when you kind of look in detail at the expressions for mobility, that it's really the phonon frequencies which are central to the temperature dependence rather than the scattering type itself. And we also looked at other things like non-parabolicity, so linear bands away from the band edges, and also anisotropy. And we found that these do modulate the temperature dependence, but nowhere near as much as the phonon frequencies. So the final thing we wanted to do is, again, these have been all model materials. We wanted to have a look in more realistic band structures. And so we generated a data set of 24,000 mobility calculations using AMSET. Now, I mentioned before that we need all of these materials parameters, so we needed to obtain them all for the materials of interest. So to do that, we just used some machine learning. So we took all of the elastic tensors, dielectric tensors, phonon properties from the materials project, trained machine learning models on these, and then fed that along with the raw band structure into AMSET to obtain our mobilities. And this is a kind of summary of the results. So if you just look at the left side, this is at 300 to 500 Kelvin. These are violin plots, so they just show you the density of your values, and on the y-axis it's the temperature dependence. And you can see that if we look at the distribution of polar optical and acoustic deformation potential scattering, these essentially completely overlap. So if you measure a material and you see a t to the -3/2 temperature dependence, there's really no way that you can assign that to polar optical or deformation potential. And this kind of, I think, agrees nicely what we've been showing before. Okay. And again, we looked a little bit more when we look at the polar optical phonon frequency across all of the materials. You can see that this basically maps on to the temperature dependence of the mobility. Here, this is a heat map, so darker colours mean darker materials, and you can see that there is some width of this distribution, and that's just showing that these band structure effects are kind of having an impact here as well, and that can vary the temperature dependence by about 0.5. And just lastly, why do we think this is important? Well, the temperature dependence of mobility has really been used to justify ascribing the factors limiting mobility to a certain scattering mechanism. And when you do that, you then actually start making assumptions about how you optimize your device. So if you're limited by polar optical phonons, the way you might optimize your device it's different unless you're comparing to deformation potential scattering. And so you can really get a very incorrect picture about materials optimization. And so I think it's very important that people have the kind of correct idea when they're trying to optimize their device. So I'm not going to talk too much about this, but people have been trying to fit horrendous deformation potentials in order to make it seem like these materials were deformation potential limited, when actually the real deformation potentials are much lower, and it's a different scattering mechanism which is dominating. Okay, how long do I have left? About 10 minutes. I just want to give one last introduction to some work that we've been doing. So this is a kind of high-level overview about the methods that we've been developing, but I just want to give one quick demonstration of how we've been using them for materials discovery. So last year, Google released this genome dataset, where they claimed they discovered 381,000 new materials which were on the convex hull. And the way they did this is they used a combination of machine learned force fields, structure searching, and some other structural substitutions to try and find some new compounds. This is a very exciting claim. Have we discovered 381,000 new materials? It would be a huge deal. So we wanted to look into this and say all they had done before was just look at the energies of these materials, nothing about the properties. So we wanted to know, are there any materials in this data set which are technologically relevant? So the property or the application that we were interested in is transparent conductors. So transparent conductors, you have them in your phone, for example, a transparent conducting oxide. These have the conflicting properties of needing to be transparent but also conductive at the same time. So in order to do this, they need to be dopable, but they also need to have a very wide band gap, about 3.2 electron volts. So with this kind of measures of high mobility, high dopability, wide band gap in mind, we set about kind of exploring the genome data set. There were some concerns which had been raised in this really nice paper by Ramshashadri. So if you look in the database, there are many materials where the oxidation states just don't make sense at all. They do not charge balance. There are lots of materials where you have radioactive compounds. So I'm not sure these are super interesting. And the other thing is, there's this entire bias towards low symmetry structures, which maybe is fine. But when you actually look at what some of these low symmetry structures are, they're like 30 oxygen atoms with one like lithium or something like that. And it's just, these are not realistic structures. A lot of them, maybe you could think of as dope structures or disordered structures, but there's some issues here. So our kind of first step was just to take this data set and do some pre-filtering. The first thing we did is just exclude all non-toxic elements because we're interested in a material which might be commercially relevant. And if it's toxic, then it kind of makes it difficult, especially if we want to put it on a phone screen, for example. It's going to be difficult to sell that. And actually, as soon as we looked at this non-toxic, this actually eliminated a huge amount of the materials. The other thing is, we wanted to run some high throughput on these, so we actually wanted to try and make the project tractable. And so we limited ourselves to materials with less than 25 sites and excluding these very, very low symmetry structures. There might be realistic monoclinic structures in there, but there were just so many of these kind of alloyed structures that we needed a very easy way to filter them out. And the last thing is we just filtered them based on their calculated GGA band gap, just to make sure that they were semiconducting, because that's what we're interested in. We're interested in a very wide band gap material. So I think it really needs to be semiconducting at the GGA level. And this actually eliminated almost all of the candidates, and we got to 627 materials. The next thing we did is just calculate their band gaps using HSE06. And we filtered out those materials which had a band gap less than 2 electron volts. Again, we're interested in materials with a band gap of around 3.2 eV. So this is quite a conservative filter. And we also calculated the band structures and filtered out the materials with high electron and hole effective masses. And this is a kind of just a distribution of the 600 odd materials that we had before. You can see that this is the filtered materials. We've got some band gaps going from 2 to 4 eV and a whole range of electron and hole effective masses. And this is just comparing them against some kind of well-known TCOs like indium oxide or zinc oxide. And we have some, comparable materials there. The next thing we did is calculate the optical absorption, and we filtered those with this absorption edge greater than 2.8 electron volts. That's just to make sure it's going to be transparent in the range that we want. And lastly, we calculated a very, very rough metric for dopability called the branch point energy. This is more of just a very rough indication of whether we think it should be dopable. And actually from this screening, based primarily on the effective masses and the band gap, we went down to just 5 candidates. So 3 N-type candidates and 2 P-type candidates. So we wanted to understand finally whether these materials that have been proposed were actually stable. And so what we did is we essentially did ab initio random structure searching from scratch to see whether we would get the same structure that the genome paper had proposed for that composition. So ab initio random structure searching is a global optimization search, which is unbiased. It's quite expensive and inefficient, but it does often work and find you the actual ground state. And what we found was that in 2 cases, the ground state proposed by Ayres was not the actual ground state. Sorry, the ground state proposed by genome was not the true ground state. And in this case, for example, we found a new ground state, which was about 100 MeV per atom lower in energy. The other issue is that we calculated the harmonic phonons, and we found that for most of these materials, these were not dynamically stable. So this is just an example where we had, an imaginary phonon mode. And it could be that we did try following these modes and trying to find the structure, but at the end of the day, we don't have very much trust in genome anyway. And so I think we need some way to filter these things out. And if we're going to go to experimental collaborators, we want to have a lot of faith in the material that we're giving them. And so we want to make sure that, making sure it's dynamically stable is a nice way of doing that. So anyway, this was the one material that came out. It's this sodium, silicon, tin, oxygen. This structure is already known. The lead version is known. But the silicon, I think it's lead and there's another A site cation. But the structure type is already known. This is a p-type candidate. It's got this hexagonal symmetry. What's very nice when you look at it is this band structure has a very disperse valence band. And so the effective masses are very low. And when we look at the mobility, which we calculated using AMSET, the mobility is pretty high. So it's about 30 at room temperature centimeters per volt second, which for an N-type candidate is very low, but for a P-type candidate is actually up there with some of the best materials that we have already. So we did manage to find something, but 99.9% of things ended up getting filtered out. Okay, so just in conclusion, I hope I've made or convinced you that these high throughput tools are very useful for material science. I guess the other point is that this genome dataset might contain something interesting, but you have to look very hard. So maybe the next Nobel Prize will come from that data set. We don't know. But okay, I just want to say thank you to all of my collaborators. Many people worked on Atomate 2, and thank you to my PhD student Ricci, who is the one that worked on the genome project. And lastly, thank you all for your attention.